going to be talking about the layout and use of a milling machine today. I'm going to start with what the different parts do. Start here. This is called the head of the machine. It has a drive motor in it, has a transmission. This is what produces the power that's used to do the work on the parts. Now, to move the parts around so that the tools that are in the head can have access to them, we have several degrees of freedom. This is a Cartesian machine, so we have an X, Y, and a Z axis. Now let's take a more detailed look at the milling machine. Here's the knee. It moves up and down on the column. Here's the saddle. It moves in and out on the knee. The bed, shown here, moves back and forth on the saddle. The head has several more degrees of freedom. The quill moves in and out of the head. And the turret allows you to position the head in order to work on pieces longer than the travel of the bed, or when you want to leave the vise in place and work on the end of the bed. Now, as the sign says, always wear eye protection when you're working in the shop. This is true whether you're running a machine or not. A student shop like this can be a very exciting place, because you can expect that 9 out of 10 of the people working at any one time really don't know what they're doing. And if you think about it that a little bit, that can be pretty scary. Stuff flying around, you may be sitting at the workbench working with a pencil and a calculator, and something will come flying across the room. So as you come into the shop, you should always put your safety glasses on immediately. So now I'm going to be talking about some of the details of what goes on in the head of the milling machine. We have an off-on switch, and here many machines will have a brake. Just turn the machine off, the machine spins down slowly. This can be really annoying if you're working the machine for any length of time. So, machines are equipped with a brake. Now, they're also equipped with a brake so that you can install and remove tools easily. Right now, we have a drill chuck installed in the machine. To remove that, we bring the quill all the way up, lock the quill in place with the quill lock, pull on the brake, and loosen what's called the drawbar. Notice I only loosen this about 1 turn. And that's because the next thing I'm going to do is beat on it with a hammer. So, if you back the drawbar off all the way so it's resting on top of the threads that are in the tool holder, when you start pounding on it with a hammer, you damage the threads in the tool holder and in the drawbar. You only need about 1 turn to give you enough room so when you strike the drawbar, the tool will come loose. Now, this is one of the newer models, milling machine. It's got a very nice feature on it. It has a continuously variable speed transmission. So to change speeds, turn the machine on, and it's as easy as turning this handle. You want a speed of 500 RPM, turn the handle down until the needle points to 500, come up to 1,000 RPM. And when you're working with very small tools, you can get a better finish and get your work done faster if you're running up at these higher speeds. Now, you see there are 2 sets of numbers on here. The outer set of numbers is for the low speed range. And to put this machine into the low range, there's a lever on the head. Take this lever and move it from the high to the low range. You'll often find that the lever won't go all the way. What's happening here is the mechanism in here is either a dog clutch or a set of gears, and you have the teeth not meshing and bouncing on top of each other. So what you do here is bring it up in contact, rotate the spindle slightly until it engages. Now this is exactly what's happening in your car when you have trouble getting into reverse gear. The teeth are just lining up like this. So by moving the spindle slightly, you now have teeth that mesh. And now you're in low range. I'm now going to be talking about the quill. The quill of the machine allows you to move a tool up and down very easily. Common uses of the quill are for drilling holes, just like in a drill press. And typically then you would use the hand feed to move the quill up and down. If you are drilling many holes, or if you're drilling holes, say, with very large diameter, so the feeds have to be very slow, it's difficult, very boring to sit here drilling all day. So what you can do is use a power feed that is built into this machine that automatically will feed the drill at a set speed. To engage the power feed, you start by engaging the quill feed lever. While you're here, notice all this information on this label. It's a good idea anytime you're working around a machine you're not familiar with to very carefully go over the machine and see what the manufacturer would like you to know about. In this case, this label says stop motor to engage. They don't want the motor running when you move this lever from disengage to engage. Also, it says disengage when not used. The intent there is to maximize the life of the gear train. If you aren't using the quill feed, you want to disengage all of the gears and shafts and bearings when you don't need them. Also, there's a warning. Do not engage at speeds above 3,000 RPM. This drivetrain is just not made to deal with those high speeds. So, now that the lever is engaged, you'll find that it doesn't always go in so easily. It can get stuck in the middle. And again, what's happening here is there is a dog clutch or a set of gears that are running into each other. The teeth are bumping each other. And what you need to do is move some part of the drivetrain so that the teeth line up like this, so they can mesh. And to do this, rotate the spindle, keep moving the lever back and forth until it moves into place and is locked in. Now we have the quill feed engaged. If we turn the machine on, you notice that this is now turning. That's part of the quill feed transmission. To engage that transmission into the quill, pull this lever back. Now if you look here, you can see that the quill is now moving down. To control the depth of penetration, say, of a drill, or the travel of the quill, there is a micrometer depth stop. This is marked off in thousandths of an inch. If you care about producing a hole that is made to a very accurate depth, you'll use this depth stop. If you just want to be close to some depth, typically when you're drilling a hole through a part and you want to make sure the drill doesn't continue through the part and say into the vise or the bed of the machine, you can use this device, which just clips into place on the screw. Now when this stop comes in contact, a mechanism disengages the quill feed transmission. Okay. You can see on the surface of the way have a very smooth surface with what are called fish scales. The little scrape marks in there. Those are to hold some oil to lubricate the way. Now, these ways are machined to within 0.005 of an inch of being flat and being straight. To take advantage, to use that precision, you have to be able to accurately locate your part relative to the tool. And to do that, we have on each axis a hand crank. And attached to each hand crank is a dial. I have a dial indicator here attached to a magnetic base. Allows me to attach the indicator to any flat ferromagnetic surface. Now what I'm going to do is turn the hand crank and bring the bed into contact with the tip of the dial indicator. Now it's come into contact. I'm going to bring the indicator needle around to 0. Now if you watch me do with the handle here, I've been turning this counterclockwise to bring the bed out into contact with the indicator. Now if I turn the handle clockwise, 20, 30, 40, 50 thousandths, if you look here, you can see the dial indicator hasn't moved. That means the bed hasn't moved. What's going on here is what's called backlash. And this is due to there being some clearance between the threads of the screw and the nut that the screw engages. To deal with this problem, you have to make sure that every time you move to a new position, you do it from the same direction. So if I bring the bed out until it reads 0 on the dial indicator, by turning the handle counterclockwise, if I want to now move the bed another 5 thousandths, I have to continue turning it counterclockwise. If I go too far, I can't just turn the handle and back up 5 thousandths of an inch because, due to backlash, the bed won't move. What I need to do is turn the handle back well beyond the travel taken up by the backlash and then come in again from the same direction. Once you have positioned a part to a desired location, you want to keep it there. And if you're using a large drill or a large mill, the forces generated are large enough to move the bed and the saddle around. So to deal with that, most machines have, they're called gib locks. They may or may not be located right here. What this is, if you can look closely in here, is just a long bolt with a handle on it. So if I turn this down all the way, I pinch the bed in the ways and lock it in place. So this gib lock locks the bed to the saddle. There's another gib lock over here that locks the saddle to the knee. And under here, on this machine, there's a gib lock that locks the knee to the body of the machine. Now, all of the degrees of freedom are clamped down. So the cutting forces produced even by a large cutter will not move the part and the axes around. Before, we were using the cranks for gross positioning. For fine positioning, we're going to be using the dials attached to the hand cranks. Say our first feature is at 0. To make calculations for later features easier, most machines have a locking ring, so that if you want your next feature to be, say, 25 thousandths of an inch away from your first feature, rather than doing a lot of adding and subtracting while you're making the cut, you can dial in with a locking ring the 25 thousandths you want and move the dial to 0 and then begin the operation. Keep in mind that repeated use of this technique can result in a significant accumulated error, because each time you reset the dial to a new dimension, you introduce a slight amount of additional error. It's often much easier when you're cutting a slot to set up the machine so that your finished position is 0. And that way you don't have to think about both what's going on with the cut while you're making chips and some fairly arbitrary dimension. So thinking about 1.3457 at the same time you're paying attention to what the machine is doing, you can easily lose track of what the number is. But if you have started out by putting in that offset to begin with, then you're simply turning the handle until you come around to 0, and then you know you're done. Most milling machines have power feeds on one or more of the axes. You can feed all of the axes by hand with a hand crank, but if you're machining all day or you're trying to get a very nice finish, you'll want to use a power feed. Some machines have power feeds built inside the machine. This particular machine has a power feed unit attached to the axis. The power feed has a forward-reverse knob, and this particular power feed has a continuously variable speed control. You should start out with all power feeds, checking how they're going to run before you start machining a part. You turn the power feed on, set the knob or the gear to 0 or to low speed, and engage the feed. Turn the knob up, and you can see the handle turning faster as I turn the speed knob up. You can hear the motor in the power feed winding down. Do that again. You can hear it spinning down there. If you're running in this direction and you go too far, if you throw the lever over to go in the other direction, you can damage many power feeds. So when you're feeding in this direction, you should stop, let the motor wind down, and then throw the feed in the other direction. Now, in addition to making your work easier, because the power feed can be turning the crank for you, you also, because the power feed can turn at a much more continuous speed than you're capable of by hand, produce a much smoother finish and flatter surfaces. Many machines are now equipped with digital readouts. These readouts measure the position of the axes to 1/2 thousandth of an inch, or conveniently switch over to metric dimensions, measure in millimeters. This in itself makes digital readout far more convenient than the dials on the machine. But the biggest feature is that having once set a position and measured it with the digital readout, you no longer have to concern yourself with backlash. You can see here as I'm turning the crank, driving the y-axis, there is no change in the number on the digital readout. This is because the y-axis is in fact not moving. And what we're seeing in the rotation of the handle here is due to backlash between the screw and the nut that's attached to the y-axis. A very important part of setting up a milling machine in preparation for doing work is making sure that the head is square. By that I mean that the z-axis of the head, the quill, is perpendicular to the axis of the bed. This operation is very much like squaring the vise, in that there are a set of bolts that fix the head in one location. There's a degree wheel that indicates the orientation of the head relative to the rest of the machine. Now, you may think that this is an operation that only needs to be done occasionally, for example, when you've tilted the head out of plane in order to machine a feature on an angle. But in fact, it's very common for example, if you're not paying enough attention, to accidentally move the vise and bump the quill. A surprisingly small force is necessary to move the head out of alignment. So before you start machining, you should always check the alignment of the vise and the alignment of the head. In order to check the alignment of the head, you can place a large parallel on the vise. The next step is to install a drill chuck or collet in order to hold a dial indicator. Now, what we're going to do here is bring the quill down until the dial indicator contacts the parallel. Just slightly. We want a deflection of about 2 or 3 thousandths of an inch. Now what I will do is sweep the indicator around and back onto the parallel. If the reading on this side is different from the reading on this side, the head is out of alignment. First, you loosen the 4 bolts that attach the head of the machine to the rest of the machine. Now the head is free to turn. As for the vise, should tighten these bolts up just snug. Enough so that it's difficult to move the head by hand, but with the use of a plastic or rubber mallet, you can gently tap on the head and get some motion. If the head is far out of alignment, for example, if you've been machining a part with the head tilted at a large angle, you need to first do a course adjustment on the head before you switch over to using the dial indicator for the fine adjustment. To do the course adjustment, you use a machinist square. Remove the drill chuck from the machine, bring the quill all the way down, lock the quill in place. Now, with the machinist square pressed up against the back jaw of the vise, we adjust the position of the bed so that the blade of the square is aligned with the center line of the quill. This does not have to be a very precise alignment. Getting within 1/8 of an inch or so is more than enough. To make the misalignment easier to see, a common thing to do is to tape up a piece of white paper and shine a light on the paper, and now you can very clearly see there is a significant amount of misalignment in the quill. To eliminate most of this misalignment, we have a transmission on the head that allows us to do a course adjustment of the position of the quill. Now watch closely as I turn the adjustment screw, and the gap gets smaller and smaller and pretty much goes away. Now, we're not quite done with alignment of the head. We have managed to get the head very nearly aligned in this course adjustment process. Now, go back to the parallel and the drill chuck. And try the dial indicator again. Bring it down into contact. A slight deflection of the dial. Swing the dial around to the other side and see if there's any difference in the reading. We're pretty close here. We're within 3 or 4 thousandths because we're getting a reading of about 6 thousandths. So now, with the hammer, tap lightly on the head. Check again. And now we're getting the same reading on both sides. As with the vise, it's very important that you carefully tighten the bolts. If you're too aggressive here tightening the bolts, it's very easy to undo all the work you've just done. Go around several times, tightening the bolts a little bit more each time. And the last step is to check and make sure that the head is still aligned. This time it is still aligned. If you have moved the head slightly out of alignment in the process of tightening the bolts, you simply have to loosen the bolts up and go back and go through the fine adjustment process again. This is an operation that takes a bit of practice. Don't expect to get it right the first time. In order to take full advantage of the precision built into this machine, it's necessary to first start by squaring up the vise. That means adjusting the vise so that the back jaw, the stationary jaw of the vise, is parallel to the bed, so that when you move a part fixed in the vise relative to a cutting tool, you are moving parallel to the part and not at a slight angle. In order to square up the vise, we start by loosening up the vise. You can see here there's a degree wheel that is useful if you want to cut a feature into a part at some angle. It's not very accurate, but if you only want that feature to be cut within about a half a degree, it's accurate enough. For squaring up the vise, it isn't even close to being accurate enough. You can move the vise over until we have the scribe mark aligned with 0. Very lightly tighten the bolts, holding the vise down. And then insert a dial indicator into a drill chuck or collet. Now bring the bed and the vise out towards me until the back jaw comes in contact with the edge finder. Now keep bringing it out until the needle comes to 0. Now with the dial indicator set to 0, as I turn the crank that feeds the bed and the vise, you can see the needle of the indicator moving. In fact, the needle has already moved over 30 thousandths of an inch. So from this point to here in the vise jaw, this jaw is out of alignment by 30 thousandths of an inch, which probably means almost 100 thousandths of an inch from one end of the jaw to the other, even though the degree marks were lined up very accurately here. What we need to do now is adjust the vise further so that we eliminate this remaining error. Now to do that, we use a soft hammer, brass, plastic, or lead, and tap on the side of the vise. And you can see while I'm tapping on the vise, the needle is moving. Okay. Tap on the vise until the needle has come back to 0. we are not yet at the point where the jaws are square. If the center of this jaw was over the center of rotation of the vise, this would be very close to being square. But in fact, the center is a little bit offset from the center of rotation of the entire vise. So in moving this edge of the jaw, we've also slightly moved the center jaw. So now what we need to do is move the bed and the vise back across the indicator. We can see now we're doing better, but we're still not quite there. Moving from one side of the vise to the other produced a change of about 15 thousandths of an inch. So, since I went from one side of the jaw to the other, I want to take about half the difference. So I've taken about half, and now I move the vise across dial indicator again. And we're getting much closer now. We're within about 2 thousandths of an inch. So just a couple light taps. Now we're within 1/1000th of an inch. Let's see if we can get a little closer. Try that. Okay, we're in pretty good shape now. There's a slight variation there, but the lines here are 1/2 thousandth of an inch apart. And you saw a variation of less than 1 line spacing. So the jaws are parallel to the axis travel to within about 2/10,000ths of an inch. Now that it's positioned that accurately, we have to very carefully, at first, tighten down the bolts. If you are too aggressive tightening these bolts, very likely that you will move the vise and have to start all over again. Cutting forces can be quite large on a machine like this. These are 1/2-inch bolts for a reason. You want to get these pretty tight, 30, 40 foot-pounds at least. Now the vise is tight. It may not still be square. The last thing you should do after tightening the vise is run the jaw past the dial indicator one more time just to make sure that you didn't disturb the alignment of the vise while you were tightening it down. Okay, that's pretty good. That is within the accuracy of the ways on this machine. Whenever you start working on a machine, you should always check the vise, keeping in mind that even though the degree wheel may suggest that the vise is square, it may not be. So you should always start work on a machine by making sure that the vise jaw is square. And also, the matter of shop etiquette, if you've been using the machine and the last job you did was cutting an angle in a part which required rotating the vise, you should never, never reset the vise using the degree wheel and tighten the vise down. You either square up the vise as the last thing you do on the machine, or, somewhat less desirable, leave the vise misaligned. And that way, it's a flag telling the next person that uses the machine, square the vise. Because if you just lock it down at 0, they may ruin a very expensive part before they realize that the vise was not, in fact, square. There are a wide variety of tools used in the milling machine. I'm going to run through some of the most commonly used tools for you now. Probably the most common tool that we're using in a milling machine is actually a drill chuck. Many of the operations you do in a drill press involve drilling, reaming, and this is the tool that we'll be using for those operations. For making more precise holes than you can make with a drill, you typically use is what's called a boring head. And this tool will allow you to very precisely locate and size holes. You'll often use this tool when you're installing bearings, where you need tolerances in the hole of less than a half-a-thousandth of an inch. This tool has a micrometer adjustment on it that will allow you to adjust the tool to 2/10,000ths of an inch. When you're beginning to make a part with a rough piece of stock, you first start out by squaring up the part, getting all the surfaces that you say have cut off with a bandsaw flat and square. The tool you do that with generally is a fly cutter. This particular fly cutter has 4 individual teeth. Another common type of fly cutter has 1 single tooth. And this tool is large enough so that the distance from here to here is over an inch. So in one pass of the tool across a part, you can flatten and smooth a surface that's 2 inches wide. So typically what you try to do with a part is choose a fly cutter that is slightly larger than the part, so that in one single pass you can produce a flat finished surface. Another very common tool that you use in a milling machine is an end mill. They come in many different sizes. Typical sizes you would use in a machine this size, anywhere from a 1/16 of an inch up to about 3/4 of an inch. Now these tools are held in place with collets. These collets are split in 3 places, and you can see there's a taper. So when these are drawn up inside the quill with the drawbar, pulled up inside the quill, this part of the collet squeezes down on the end mill and holds it in place. For end mills larger than 3/4 of an inch, what you need to do is use an adapter like this. It's commonly used with end mills with shank diameters of about an inch or so. Put the tool in the adapter, lock the set screw down, tighten it securely with a wrench, and then insert the tool and the adapter into the milling machine. A very handy tool to use. You want to make relatively deep, narrow slots in a part is a saw. And these saws are installed on an arbor. Saws come in many different diameters, many different thicknesses. And in fact, for some operations, you can install several saws all in the same arbor and cut 2, 3, 4, 5 even slots at the same time. Another operation that's commonly performed milling machine is reaming a hole. After you've drilled a hole, you have a fairly rough surface and a not very well-defined diameter to the hole. So you run a reamer through the pre-drilled hole. A reamer of this size is typically inserted into a reamer adapter that then is inserted into the machine for reaming. Here is a very handy tool. This is a combination edge finder at this end for finding the edges of parts so you know where the part is relative to the machine, and the other end is a center finder. So if you've used a center punch to mark a feature in a part, or you already have a part, say, that has holes drilled into it, you can use this taper to locate that feature. The remaining tool is a 3/4 inch shank boring tool. Larger tools can be used in a large boring head that, in addition to allowing you to bore holes up to about 4 inches in diameter with a tool in this orientation, also allows you to insert the tool in the side of the boring head and bore holes up to 1 foot or more in diameter.